Yeah, what I do when I have a bad one is I throw it out. Okay. And what do I do with this? Find the max. Maxes, okay. So, lovely. Really? I gave this problem? Oh, okay. So where are these zeros? I'm just, like you, I haven't seen this in a long time, so I'm starting from scratch and I'm gonna wander around and see if I can find a solution. Oh. Cosine 2t. So I can express that in terms of sine or cosine. So that's what I want to use. I'm setting this equal to 0, so I'm going to forget about this factor here. This can just go away. So I have sine t minus 1 minus 2 sine squared t. I want to set that to 0. So what do I end up with? Let's multiply through by minus 1. No, that's not what I want to do. I want to distribute the minus. So I have 2 sine squared t plus sine t minus 1 equals 0. This is a quadratic. It's like 2x squared plus x minus 1 equals 0. So I could either try and factor it, or I could use the quadratic formula. Negative b plus or minus the square root of 1 minus 4 times 2 times 1, which is going to make it plus 8. So you can already see we're on the right track. Not because we're doing math right, but because they put problems that work out nicely over 4. So that's negative 1 plus or minus 3 over 4. So that's minus 1 for here. So we have either sine of t equals -1 or sine of t equals a half. That's where the derivative is 0. That's where the max and mins will be. Now, we're only looking from 0 to pi over 2. So let's take a look. Where is the sine -1? That would be over here. So that's out. Sine could be a half. And that is a 30-degree angle, or pi over 6, which is, does fit there. So that tells us that whatever this thing looks like, it might be good to look on your calculator or on Desmo to see what it looks like, but Rich did between 0 and pi over 2, and at pi over 6, there's going to be, well, let's see what the value is at pi over 6. 2 cosine pi over 6 plus sine pi over 3. Can we just find out what pi over 3 is? No. Kind of with sine of pi over 6. Okay. All right. So cosine of 30 degrees is square root of 3 over 2. Sine of pi over 3 is at 60 degrees. That's going to be square root of 3 over 2. So it's going to be 3 square root of 3 over 2. So at pi over 6, we have, what's up here somewhere, 3 square root of 3 over 2. And we know this is, the derivative is 0 at that point. So then we have to check, that's a, we don't know yet, but it's a relative max or min. We want to find out the endpoints. So cosine of 0 is 1, so this is 2 plus 0. So 0, this is going to be 2. So now I actually want to know what this is. So 3 times 1.7, 1 divided by 2, 2.5. Okay. So this, at pi over 6, it's about 2.5. At 0, it's 2. So we can kind of see what's probably going to happen. And then at pi over 2, okay, let's find out what this is at pi over 2. So the cosine of pi over 2 is 0, so that's 0. Sine of pi over 2, oh, 0. So here is 0. All right. Okay, so now we know, I think, everything we need to know to answer the question. What's the question? Max and mins? Okay. So this is both a relative and an absolute maximum at pi over 6. And the min is at pi over 2. It's kind of sloppy, but I didn't prepare. Hard mostly because you have to know your trig and your trig identities and your trig values. I don't know what it is. It just feels beastly hot, warm right now. And I know as soon as I take off this sweatshirt, I'm going to get cold. But there any other homework problems that people have? Was that like the hardest one? Or was that just an example?
For personally, it was the hardest one.
Okay. Oh, there it is. Okay, can I erase? And thank you for bringing that to our attention. So, I don't feel very good about what I did on Tuesday. I feel like I communicated well this idea that this chapter is about trying to describe the shapes of functions using derivative. So I kind of thought it through again, and this is, of course, we're still hovering on section 4.3, derivatives and the shape of the graphs. And what I decided was, I mean, there's kind of this thing going on in my head. There's a lot of things going on in my head. I didn't sleep well. So, careful attention, catch me on errors. But I thought, we have all these graphing devices. It's not trying to take a look at the graph of something is as simple as punching it into a TI or Desmos if you have a computer. And so what I decided is I'm going to look at this kind of backwards. We're going to take a look at the shape of a graph, and then we're going to see how the derivative kind of tells us what we're seeing, is what it is. So before I give the first example, I just want to iterate here. I want to list the tools we have that allow us to do this. The first thing we have is the roots. The roots of a function is where it's going to go through the x-axis. We have ways to find roots. Next, we know that if f prime of x on an interval, write that, then the function is increasing. If f prime of x is greater than 0. If it's less than 0, it's decreasing. And if it's at some point it's 0, then we have a max, a min, or we might have neither. Just a quick example. F of x equals x cubed. Kind of looks like this. Derivative is 3x squared, and that's 0 and 0. Well, we don't have a max or a min. We just have this point here we're gonna talk about. We have the first derivative test. If I'm going too fast on any of these, slow me down. I think we went over some of this, but I'm just trying to kind of make it available to us for the next portion. Derivative test. That says f prime of x goes from positive to negative at c, then c is the maximum. We want to kind of, have a visual or, kinesthetic kind of feel for that. the derivative is positive, right? That's a line going up, up from left to right, and it goes to negative. So between these two, it's going to have a maximum. If f prime of x goes from negative to positive at c, then c is a minimum. Then we have this idea of concavity. It says if the second derivative is greater than 0, well, the second derivative is 0, first derivative is increasing. So it's like going from negative to positive. Again, it's good to have kind of either a visual or a kinesthetic feel. That means we're concave up. And if the second derivative is less than 0, concave down, for the same reason, going from positive to the negative slope. And if f prime of x is equal to 0, we have a point of inflection. There we go. That's a point of inflection. Goes here, it's concave down. Here it's concave up. It just happens to have a derivative of 0 at that point, but it doesn't have to. We'll see graphs that kind of look like this, where the derivative is not 0, but you have a point of inflection where the concavity is changing. I think I'm waking up. Okay, and then finally we have the second derivative test. It says what? If the first derivative at some point is 0, and the second derivative at that point is greater than 0, and f of x has a local min at c. Okay, let's think about that. You've got you've got a derivative of 0, right? So it could be a max. Where does it say this? Could be a max, could be a min, could be neither. But the second derivative is positive. That means the first derivative was increasing, right? So again, kind of think of this in either visually, or you can move your hand if you want. The derivative is increasing because the change in the derivative is increasing. So the slope is increasing, so we get a minimum. Likewise, derivative is 0 is less than 0. For the same reasons, we have a max. That's C. And if the derivative is 0, and the second derivative is 0, then again we have a point of inflection. I want to put in parentheses, point of inflection, typically place where concavity changes. Okay, so it's going to take me a minute here, because I want to do an artistically valid rendition here. Take a couple of tries. This is f of x equals the sine of x. So here's pi, 2 pi, 1, -1, and it's going to go like this. Next, we're going to look at the derivative, which is going to be the cosine of x. I thought this out in my, not in my sleep, in my lack of sleep. I want to do this. Let's see if it'll actually work. So, guess I need to draw it first. Pi over 2. Pi over 2. So it's going to go like this. Okay. What I want to do here is where it's positive, one blue, where it's negative, I want to do it in red. We'll come back to this. And again, I'm going to do the second derivative of x, which is negative sine of x. If you have trouble seeing this, Lisa, move. That's how you can see it. Okay, again, pi 2. And so this one, I'm going to do, again, orange for the negative, and I get to use all these finally. Green. Okay. Now we want to take a look at this. All right? If the derivative is greater than 0, then the function is increasing. Let's look here. This is where the derivative is greater than 0. Let's look at the function here. What's happening? This is where it goes up from 0 to 1. Where it's decreasing. Where f of x is, where the derivative is less than 0, it's decreasing. Okay, this is where the derivative is negative. It's saying what value? It's negative. What happens to the derivative? Well, it's decreasing. And it continues to decrease. And again, here where the derivative is positive, we see it's increasing. We want that to seep in, right? This is just a feature, something useful you can get out of first derivative. Now, let's look at, I'm going to color code this here. This is red. This is blue. Let's take a look where the derivative is 0. Well, that's this point over here. This point over here where the derivative is crossing the axis. What do we find? Well, it looks like the maximum. Looks like the minimum. The local max or minimum. See how we're connecting these? Every everything here is reflected, is going to be reflected over there. Okay, first derivative test says if the derivative is going from positive to negative, it's a maximum. Derivative is going here from positive to negative, it's a maximum. Derivative is going from negative to positive, it's a minimum. So you see all these rules, just they apply directly. All right, let's talk about concavity. Second derivative is greater than 0, it's concave up. Well, that's over here. And the function is concave up. Where the second derivative is negative, again below the x-axis, this is concave down. This is, takes a while to kind of seep in. You can just kind of iterate the rules and then have to think about how they apply. Okay, finally, where the second derivative is 0, we have a point of inflection. And this took me years to kind of see this and have a feel for it. Well, it's 0 here at 0, second derivative. It's here at pi, and pi over 2. Well, here's our, I can draw the graph further, but let's just look at pi. What happens here? It's concave down, and this is exactly the point where it starts to become concave up. That's our point of inflection. I abbreviate. Oh, we have a little, we're not quite done yet. I guess I'll color code these. Green, and this is the orange. All right, so I think we've already gotten all the information, but let's just check this second derivative test. It says, where the first derivative is 0, then we're going to look at the second derivative, see if it's greater than 0 or less than 0. So here the first derivative is 0, but the second derivative is negative, it's less than 0. So that says it has a max. It has a max. First derivative is 0, but the second derivative is positive. That says it should be a minimum. There's the minimum. And finally, if they're both 0, we have a point of inflection. I'm sorry, that's not right. That's not right at all. If the second derivative is 0, we have a point of inflection. So that's here, and that's our point of inflection again. Now, could we go the other way? We take a function, find the first derivative, find the second derivative, and apply these rules and get a feel for what it looks like. Yes. Is that an important skill? I just don't see it anymore, Just like I was in high school, we learned to use slide rules in chemistry so we could multiply really quickly. Now, I know that sounds like the Stone Age. We did not have handheld calculators. There was a few mechanical ones in the business office, and we had a little computer terminal you could do basic on, and that was it. So we used the slide rule, and we were testing. You had to do it fast, and it was a skill. Drawing a graph, a necessary skill. think you have to understand what derivatives have to do with the graph. I don't see that. So, all right, any questions about the sine function? Because we're going to do another one. Yes?
So at what point does it start switching from like positive to negative to positive? Does it start like,
The first derivative?
yeah, the first derivative?
Well,
Does it start once?
again, this is the x-axis.
Yeah.
Y is, above the line is positive, below it's negative. So here it's going from positive to negative. It goes through 0.
Yeah, so then I'm wondering just, for when it switches from negative to positive,
Negative, okay.
would it start, like, once it becomes negative, if that makes sense? So is the entire red line, that entire red line is...
Yeah, the entire red line, the first derivative is negative. So it's a decreasing function. From here to here, it decreases, right? The points where it's 0 are the points where you have the local max and min, and it's changing direction.
Okay, so it doesn't start changing once it hits the local minimum, if that makes sense?
The derivative goes to 0, the local min, and changes. Yeah, that's kind of this first derivative test. There's some overlap here. There's some duplication, right? I hope that's not confusing. In some circumstances, there might not be overlap, or there might be some further differentiation we need. Yes?
Same kind of question. So if C is a single number, a single point, then how can it be going from positive to negative or negative to positive?
The derivative is going positive to negative at C. So, at some kind of interval, if this is C, right, pi over 2, the interval around it is going from positive to negative. I mean, we're dealing with very nicely behaved, smooth functions that aren't doing ugly things. That's for another math class, I mean, you might have a point, you might have a function that where, it looks like it's going positive to negative, but then it kind of gets schizophrenic in here,
Sure.
You might not be able to apply this rule.
So if you had x squared plus 3x plus 1, which is 2x plus 3.
I'm sorry?
2x plus 3 would be the first derivative, right? Yeah. So how can you tell that 2x plus 3 is going from positive to negative?
Oh. Well, let's find out where it's 0 first. Oh.
In the book, I think they just
Does it have any roots?
I think they just did a quick table in the book. They just used like a little table in the book. I think they just
You could do a table, yeah. I'm not sure if this is a good example yet.
So you just have to plug in random values for x and just...
I don't like this example. I'm going to fix your example, all right?
Okay.
So we'll say x squared minus 2 plus x. So that's, hopefully that's x plus 2 times x minus 1. So that's going to be a parabola that it's going to be minus 2 and plus 1. It's going to look like that. And let's find its derivative. And if we set that equal to 0, we get x equals negative 1/2. Negative 1/2. Okay, so we don't know what the graph looks like yet. I'm happy to know what it looks like. So you could take a point, let's say, negative 3/4, and you could take a point 0. So let's look at those. F of 0, that's easy, it's -2. I should have, I have to write that second. F of 0 equals -2, and F of -3/4, what's that? That's 9/16 minus 3/4 plus 2. 9/16 minus 12/16 plus 32/16. So 41 minus 12 is 29/16. Well, we didn't actually have to know the value, we just need to know it's positive, right? So, wait, I forgot, yeah. So it's positive. So what's happening? It's going from positive to negative. Yes, I've done something wrong here. Anyone catch my mistake? Oh, it's the derivative, where the derivative goes from positive to negative, where the function goes from positive. We know the function can do anything at that point. All right, let me try again. F prime of -3/4 is -6/8 plus 1 is 2/8. So it's going from some positive number, 1/4, and F prime at 0 is 1. Again, I've done something wrong. Oh, I can't multiply fractions anymore. -6/4, -2/4. I would be making terrible errors. So it's going from negative to positive. So negative to positive, it's the minimum. That's the process. Yes?
I might have missed this, but where did you get the -3/4 from?
Okay, the roots are at -2 and 1. And the derivative is 0 at -1/2. So I just arbitrarily picked 2 points
Oh,
between here. I mean, 0 is always a nice one. It's nice, easy to plug in. And I just had to go with some fraction over here. So between these 2 places, I know the derivative is going from negative to positive. Now, I wasn't particularly close to the point. In a function, you might need to get closer because, again, some weird function might, be jumping around here. But in this case, polynomials are smooth, they're predictable, they're nice functions. This is good. I want you to think about this because this is if you just do the mechanics, you can go very far with just the mechanics. If I give you some complicated function and you can find its derivative, that's good. But when you're faced with a problem, a real-world problem, you want to know if the answers you're getting make sense. I mean, I've already made a couple mistakes here, but I immediately saw, no, that's not right. Let's go check. All right. So this is going to help you understand what this is all about. Now, this is a great example. It's beautiful. It shows this this weird idea that somehow doing derivatives of sines and cosines, you just end up with another function. It's just a phase change. I don't know of any other function that has this property. So we're gonna look at something a little more edgy. We'll have some complication. Okay. I don't know how I'm going to fit it all in, but I will somehow. All right. So the next function we're going to look at is just something, I think this is from the book.
So f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5.
It's a polynomial. It's even. It's degree 4. We suspect whatever its end behavior is, whether it kind of goes up on one side, it'll go up on the other, or down on both sides.
I guess I'm just going to draw the graph as best I can. 5. I'm distorting the scale so it'll fit. I think this is -1. And then 1, 2, 3. Comes down this way to about -27. And then it's going to loop back. Okay. So that's our function. I'm going to digress for a second, just because I know not everyone's basic algebra skills are some of them are a little weak. I'd say, how would I find the roots to this? Well, we actually have the tools to do that. We could spend a lot of time doing it. What we would use here, I mean, if it was obviously factorable, we would do that, but it isn't. So we would look at this, and we'd see the coefficient here is 3, the coefficient here is 5, and then there's a whole range of potential rational roots. The rational root theorem tells us that a potential rational root has to be a factor of 3/5. So it could be 3/5, it could be -3/5, it could be 1/5, -1/5, it could be 3, -3, and it could be 1 and -1. And we can spend a lot of time just plugging them in, see if they're roots. Or we can cheat and just notice. So if I plug in -1, I get 3 plus 4 is 7, plus 5 is 12, minus 12 is 0. So -1 is a root. Then, either using synthetic division or long division, I can divide out x plus 1, and it's unimportant what I get. There's another root in here. There's another -1. And so this becomes x plus 1 squared times 3x squared minus 10x plus 5
Well, now this is a quadratic. We can use a quadratic formula. And if you want to apply it, you'll find that the solution is 5 plus or minus square root of 10 over 3, which is approximately 0.6.13, 2.72, which are these points here and here. There's my -1. This is common when you have a double root. The polynomial tends to just kind of, hit the axis and go up, or come up from below and go back. Okay, so that's the roots. That's the first thing we know about. If you were just trying to figure out what this function looked like without a calculator, that would be the first thing, is to just mark these points, say, well, I know it's going to go through them. All right. Well, next we want to look at the derivative. So the derivative of this function, well, we really only need the power rule, right? So it's 12x cubed minus 12x squared minus 24x. We're really not that interested in, we're gonna see where this is 0, but we're really not that interested in the actual, the quantitative value, just whether it's positive or negative. So we can divide by 12. And what are we going to get? We're going to get x times x squared minus x minus 2 equals 0. Does that sound right? And that's what? X times x minus 2 times x plus 1. So the derivative is 0 at 0, -1, and 2. It might be better to put in order. Okay. Well, let's take a look. Sure enough, at -1, there's you can see there's a minimum. We're going to investigate a little further. At 0, there's a maximum. And at 2 over here is another minimum. Just knowing this, we can plug these values into our function and find these points. We still wouldn't know really, what the graph kind of, well, we actually we'd be pretty close at that point. All right, let's apply this increasing-decreasing test here. We know that these points are going to divide up the x-axis into intervals where the derivative is constant. I mean, it's smooth, it's continuous. This is where it's 0. So we're going to have an interval -∞ to -1. We're going to have an interval -1 to 0. We're going to have an interval 0 to 2, and an interval 2 to infinity to investigate. We want to know what the derivative is at these points. Well, pick any point you like -2, plug it in, and what are we going to find? Well, this would be a good moment, I think, to draw the derivative. That's this function. It's going to -2. I encourage you, if you have a calculator or a computer, go to Desmos or plug it in, plug in this function, and check whether I'm telling you the truth here. This is what the derivative is going to look like. again, I want to color this. Okay. It's more normal, but it's a little trickier than the sine function was. So this is obviously -1 here. The derivative is less than 0. So it's a decreasing function. From -1 to 0, it's positive. So it's an increasing function. I guess this point, what's this point? He decided it was 0.613. From here down to 2, the derivative is negative, so it's decreasing. And from here on, the derivative is positive, it's increasing from 2 on. So we're seeing the same pattern, right? This. We could pick a bunch of points and show that, this is a minimum, this is a max, and this is a minimum. For some arbitrary function, you might want to do that. If it's a polynomial, this is what polynomials are like. They're smooth, they have bumps, they don't do anything crazy. So the fact that it has a 0 at -1, and we know off in this direction it's going to get large, we know that it's going to switch here, and it's going to switch up here, and switch down here. This will be a minimum, local maximum, local minimum. I don't want to, I would just be throwing lots of weird numbers up. Okay, let's talk about concavity. We need to know the second derivative, right? Second derivative is the derivative of the first derivative. So that's going to be 36x squared minus 24x minus 24. I don't know what's right here. Second derivative of x. And if we want to set that to 0, well, let's divide out by 12. That's 3x squared minus 2x minus 2. And what happens when we apply the quadratic formula? Again, I'm going to cheat here, because x is going to be 1 plus or minus square root of 7 over 3, which is going to be about -0.55 and 1.21. Okay, what is this? It's where the second derivative is 0. That's the points of inflection where the concavity changes. I guess I should draw this. I'm going to leave out the factor of, again, 12, because it's not relevant here. And this graph is a parabola. It's going to be -2 at 0. Jump through here, and through here. So this is my point -0.55, and here's my point
what was it, 1.21. Well, now you have to kind of sharpen your eyes a little here. 0.55 in here, you have a point of inflection. The concavity was concave up here, it goes to concave down here. And at 1.21, that's down here somewhere, this happens again. It's concave down, becomes concave up, and remains that way for the rest of the function. So again, that's I'm not going to apply everything here, but that's the application here. I guess I'm going to complete this. This is these are my green positive places. My negative orange places. And again, they show you where the function is concave up, concave down, and concave up again. You want to think through that when you're doing the homework. What does the derivative have to do with the shape of this graph here? So, okay, I think good time for a break. Any questions for? Yes.
When you're doing the quadratic formula, why is it 1 plus or minus the square root of 7 and not 2?
A fair question. Maybe I made a mistake. Let's see. Quadratic. Negative b, so that's 2, plus or minus the square root of 4 minus, but since it's a minus, it'll become plus. 4 times 3 is 12, times 2 is 24, over 2a. So it's 2 plus or minus the square root of 28 over 6. I'm going to divide the top and bottom by 2, so I get 1 plus or minus, this is going to be 3, but under the square root I divide by 4.
Oh.
Okay?
Cool.
All right, any other questions? I'm going to leave this up, so if you have any questions in a few minutes, we'll take a look at that. And take a walk for a minute. Okay.
Okay, are there any questions about this? Anyone think of something you want to ask before we move on? Yes?
Yeah, that's a question. I just wanted to know if you could go over the first derivative, like how to sketch it. I get the calculations, it's just how to sketch it.
The derivative or the second derivative?
The first,
First.
yeah.
How did I get this?
How do you draw it?
Oh, how do I draw it? Oh. Well, you mean how do I know it looks like this?
Yeah.
I cheated. I just plugged it into Desmos. I mean, we could adopt the same process. We could start with this function. It's a function, right? We can find its first derivative and find the max and mins, the roots, everything we do with the more complicated function.
Okay.
You know, I mean, there's always, you can plot points. That's what the graph.
Yeah, we can get a point, but how to know if it's
Yeah. Well,
Wherever the derivative is.
well, let's look at this. Can we, well, once we factor it, it's a polynomial. It's an odd polynomial, which means whatever it does on one end, it's going to do the opposite on this end. The leading coefficient is positive, so when it goes to the right, it's going to be positive and negative to the left. These are basic things about odd polynomials. It has roots 0, 2, and -1. So we know it's going to go through here. I can find its derivative and find out where the local max and min are and find the values. That would give me 1, 2, 3, 4, 5 critical points. Wrong word, because that means something. Crucial points, right? And then I can just hand plot. Or I can plug it into Desmos or your TI calculator. Again, as I said, I think you were here. As I said in the beginning, I don't feel like, taking this function and, using all this information as the basis to draw a graph is an important skill. It's a useful skill if you're on a desert island and don't have a calculator, right? But knowing, the relationship, between the derivative and the second derivative and the function, I think that is important. And that's what I tried to emphasize. Okay, any other questions?
Is the rational root theorem, is that just some algebra?
That's a pre-calculus thing. If you want to go over it sometime in office hours, I'll show you. It doesn't say, the rational root theorem doesn't necessarily get you anything. What it gets you is if a polynomial has a rational root, it has to be one of these.
Okay.
So, if it turns out that they're all, they all have roots, or worse, they're complex, it doesn't do you any good. Well, I'm going to digress for just a second. This is totally unimportant for this class, but if you're interested in math, it's useful. So we have a quadratic formula. There's a formula for third degree. You can Google it. There is a formula for fourth degree. They're very ugly. The third and fourth are very ugly. You want to exhaust your other possibilities before you ever try it. But, pushed, you can look up the formula and you can always find the roots. Fifth degree, some fifth degrees you can find the roots, but there's no general formula.
that curious fact that was being investigated in the 1700s was the precursor to an entire branch of mathematics, which is, if you go on in mathematics, it's called group theory, and it's kind of at the bottom of algebra. All algebra starts at groups and, moves on, and you get polynomials and linear algebra and all sorts of fun stuff. But it's an interesting problem. Galois, one of those, there are a few of them, these mathematicians who do like all their work by the time they're 21, and they're famous, and then they get sick and die because the 1700s medicine isn't quite as good, or sometimes it's a duel. Crazy. Okay.
What mathematician had a duel? What mathematician died in a duel?
I think it may have been Galois, actually. He was like, stirring the night before, I have this great idea for this theory. We'll call it, we call it Galois theory. And I think he died in a duel. But I could be wrong, because G.A.
Write down a letter to the student and just wrote down his theory. It's like, I'm gonna do
Math,
tomorrow,
yeah, the
just
important
write it
stuff. All right, homework assignment. No. Google Galois. French, probably. All right. I'm going to erase the board, which will give you a minute or two to ground yourself so you don't get whiplash. Because we're going to embark on an entirely new subject, one many of you will really like. It has to do with finding limits. I made a reference to the fact that, I know you may not like doing limits, but if you can do derivatives now, you're going to be happier than you were at the beginning of class. We're going to, well, again, let me try and avoid the whiplash. There you go. Okay. We're going to learn about what's section 4.4 in Stewart, and it's known as, my best French accent, Lopital's rule. And since all over the internet and math books, they spell it two different ways, I guess there's a silent S here. Again, a Frenchman. Lopital's rule is useful for finding some otherwise difficult to find limits of a certain form. It's going to make it, now that we know how to do derivatives, it's going to make it easy. But there's a mistake that all students, not all students, there are always students who make this mistake. They don't listen when I say you need an indeterminate form. So before I talk about Lopital's rule, I'm going to talk about what an indeterminate form is. I guess I can write this here. I spelled that right, form. So, if you have some limit, say x approaches 3x, there's nothing indeterminate about this. polynomial, it's continuous. The limit is the same as the value of the function. At that point, it's going to be 3. No problem. If instead we had something like this, x approaches 1 of, say, x squared minus 1 over x minus 1. Well, the numerator goes to 0, and the denominator goes to 0. So we're not really sure what's going to happen yet. Well, you might actually know, but that's what an indeterminate form is. There are a few of them. This is the most common one, 0 over 0. That doesn't mean 0 over 0 is obviously not defined. It's not a number. But our limit may be going there, and we don't know what it is yet. Other indeterminate forms are infinity over infinity. Again, not a number, but an indication. You have a fraction, the limit, the numerator is going up, the denominator is going up. You don't know what's going to happen yet. You might have negative infinity over infinity, or infinity over negative infinity. Again, indeterminate forms. There's a few others. Might as well get them out here. There's infinity raised to 0. Now, again, not a number, but you've got a base that's getting larger and larger, and an exponent going to 0. Think about that. We don't really know where that's headed, where that limit is headed. We could have 0 raised to infinity. That is, we've got a base that's going to 0, but the exponent that we're raising it to just gets larger and larger. Okay. This could go to 0, it could go to infinity, it could go to some number. Same here. All these are indeterminate. Oh, there's 2 more important ones. 1 raised to infinity. Well, usually 1 raised to any power is 1. But this is a limit. We're moving towards 1, and the exponent is moving towards infinity. And so, again, it could go to 1, could go to infinity, could go to some number. And finally, the last form is 0 to the 0, which, as you know, 0 is not defined as a number, but we could have a limit where the base goes to 0 and the exponent goes to 0. You might have to think about that for a second. Like, some number that's not 0 to the 0 is 1, right? But 0 multiplied by itself any number of times is 0. So we don't really know what the limit's going to end up with. Now, I can't say this enough times. You cannot use Lopital's rule unless you have an indeterminate form. Every year, I put a problem on the exam, a limit, and it's not an indeterminate form, and people use Lopital's rule. You always want to check. You want to make sure that, like in this case, clearly this is an indeterminate form. This is not. This is not. This is going to 0, but this is going to 2. This is easy to evaluate. This is, the limit here is 0. Keep that in mind, please. I'll repeat it. I'm going to repeat myself. Okay, so
this for a minute. All right, so we're going to develop L'Hopital's rule, or at least we're not going to completely prove it, but we're going to show where it comes from, give you some kind of algebraic view of why it might be so, because it seems pretty peculiar. We'll say what it is for a little surprise in a minute. What we're going to start with is the definition of a derivative of a function. It's the limit as h approaches 0, f of x plus h, should be familiar, minus f of x over h. An equivalent version, which we don't use as much, which you can get by substituting, we substitute x minus a for h. We're going to get the limit as x approaches a of f of x minus f of a over x minus a. This actually looks a little more like delta y over delta x that you're familiar with. Now, we consider two continuous functions, f of x and g of x, with the property that f of a equals g of a equals 0. And we assume that the derivative of g at a is not equal to 0. And then we want to look at the falling limit. This is, this kind of comes out of nowhere, but you just have to kind of go along with it and see where we come out here. We want the limit of the derivative of x over the derivative of g as x approaches a. Okay, so we have to apply our limit formula here to find out the derivatives. Well, this is the limit as x approaches a of the limit as x approaches a of f of x minus f of a over x minus a, limit x minus a of g of x minus g of a over x minus a. Again, I'm just applying our formula to f and our formula to g to evaluate this limit. And you can see we don't really need this limit here. Every x is just going to a everything. So we can simplify that. Well, this is just the limit. I'm going to have to continue in blue. This is dead now. This is the limit as x approaches a. This is using our limit laws. F of x minus f of a over x minus a, g of x minus g of a over x minus a. And again, applying our limit laws, we can take out these two factors and put them together. And we get the limit as x approaches a of f of x minus f of a
g of x minus g of a times the limit as x approaches a of x minus a over x minus a. Hopefully you've seen something like this before, or you recognize it. This is a limit. We can't evaluate it at a, it would be 0 over 0, but clearly the limit is 1, right? So we can just, eliminate this, it's 1. All right, let's go back. Our assumption was that f of a and g of a were 0. So what do we have here? We have the limit as x approaches a of f of x over g of x. Now, this is not what we wanted to end up with. This is where we wanted to start. We want to know about a limit that's indeterminate, right? F of x, because it goes to a is equal to, well, it's equal to 0. So this is going to 0 over 0. But where we started is here. The derivatives. This is saying that to evaluate this limit, which is indeterminate 0 over 0, we can evaluate the limit of the derivatives, the quotient of the two derivatives. So let me write that over here. This is Lopital's rule. Limit. I'm not gonna forget. If the limit as x approaches a of f of x equals the limit as x approaches a of g of x is equal to 0. In other words, the limit of f of x over g of x approaches a, it's approaching 0 over 0. This is equal to the limit as x approaches a derivative of f of x over the derivative of g of x. That means that if we have this indeterminate form, f of x over g of x going to 0 over 0, that we can try evaluating this limit, the one with the derivatives. And that's going to turn out to be exceedingly useful. All right. I feel like I want to keep this up, but maybe there's no room. Keep this up as long as I can. Let's do a simple example. This is the limit as x approaches 1. The natural log of x over x minus 1. There's a limit we'd be hard-pressed to know what to do with before now. Probably the best we could come up with is, well, you can graph it, see what the graph looks like. There's the graph heading for some value. But Lopital's rule says, since log of x, log of 1 is 0, and 1 minus 1 is 0, this is going to 0 over 0 in indeterminate form. And this is going to be equal to the limit as x approaches 1 of the derivative of the log of x over the derivative of x minus 1, which is what? Derivative of the log of x. Anyone? This should be on your list. Right? Very important. 1 over x, and the derivative of x minus 1, that's just 1. Okay. So this is just the limit as x approaches 1 of 1 over x. Well, that's just 1.
I'm not going to take the time to try and bring up this computer and show you the graph. You might want to do that on your own after class. Just graph this, put it on your TI, and see what happens. You're going to find out, it's undefined at 1, but the limit is clearly 1. Now, we only developed it here for that indeterminate form. And I'm not going to go through and prove Lopital's rule for each of these, but we'll do some examples here. Okay, we want to know the limit as x approaches infinity of x squared minus 1 over 2x squared plus 1. So the first question we ask, if we want to use Lopital's rule, is this an indeterminate form? Well, the numerator is x. As x goes to infinity, x squared certainly goes to infinity. The minus 1 doesn't matter. And as x goes to infinity, 2x squared plus 1 certainly goes to infinity. Line to infinity over infinity. Check. We can use Lopital's rule. So, we find the derivatives, 2x over 4x. Okay. Now, this is still an indeterminate form. 2x is going to infinity, 4x is going to infinity. Okay, we can apply Lopital's rule again. No, not a problem. The limit as x approaches infinity, 2 over 4. Now we solved this in a different way before. We evaluated it a different way before, but this is just clear as could be. As long as you check it's the indeterminate form. This is kind of a boring example. They're really good examples you're going to see. All right, let's try an example, a non-example. What's the limit as x approaches 0 of x plus 5 over 2x plus 5? This is a non-example. We don't need Lopital's rule. Neither of these go to 0. They're both just a rational function. The limit of the numerator is 5. The limit of the denominator is 5. We know this is 1. Should you not check that this is an indeterminate form, which it is not, and you apply Lopital's rule, you're going to get, oh, this is 1 over 2 is the half. And you know, wrong. Don't do it. Always check. Okay, now, as I said, that was kind of a boring example. This is kind of an interesting example. There are a lot of really, really interesting examples. Things that I'm sure keep you up late at night wondering what the limit as x approaches infinity of e to the x over x squared might be. e to the x, as x gets larger and larger, it's going to infinity. X squared, clearly the same thing, right? So, I'm just going to answer for that. This is going to infinity over infinity, so we can use Lopital's rule. Tells us derivative of e to the x is e to the x. Derivative of x squared is 2x. We have that problem again. Still indeterminate. This is going to infinity, this is going to infinity. So again, we can apply Lopital's rule. E to the x over 2. All right, now we can see our original limit is infinite. It's just getting larger and larger. Wasn't obvious at first, now we know. All right, a lot of problems are just simple like that. You just apply the rule, find a derivative, and you find a solution. Sometimes you have to work a little. You have to think about how we can get this to work. Now, I'm doing here a limit from the right, and I haven't shown that Lopital's rule works for one-sided limits, but it does. You can just take that on my say-so. We have the function x times the log of x. Right. That's not so obvious what we do with that, is it? But we can rewrite this do a little work. We can rewrite it as log of x over 1 over x. Everybody happy with that? As we go to 0, what does this go to? What does the natural log go to as x goes to 0? 1. The log, this is the log of 0. We're thinking it's undefined. You're thinking the log of 1 goes to 0. This is the opposite. This is going to negative infinity. As x goes to 0, what does 1 of x go to? It goes to infinity. We can use Lopital's rule. All right? Derivative of log of x is 1 over x. Derivative of 1 over x, well, that's x to the minus 1, so using the power rule, the derivative is negative 1x to the minus 2. Okay. What's this? This is negative x. As x goes to 0, negative x goes to 0. So once again, we have an indeterminate form, and Lopital's rule allows us to evaluate it, and we can see it goes to 0. Again, I encourage you to try this with a calculator or Desmos. It's a good way to check your homework too. Like, you use Lopital's rule and you get a value. How do I check this? You can graph it and see what happens. Oh, darn. I forgot one.
if I have two, I have a limit, which is a difference, and each term goes to infinity, they're both getting larger and larger, we don't know what's going to happen. One might get larger much faster, and it'll go to positive infinity. One might, the other might get larger much faster, and we go to negative infinity. Might go to 0, might go to some value. So let's see how we can apply Lopital to one of these problems. So we want to know the limit, again, a one-sided limit, 1 over log of x minus 1 over x minus 1. I'm going to run out of time. I'm going to finish this one up, and then we'll do a little more next Tuesday. Okay, so log of 1 is 0. This is going to infinity. 1 over 1 minus 1 is going to infinity. So we can apply the rule. But again, we still need a fraction. So let's put these over a common denominator. X minus 1 minus log of x. Log of x minus x minus 1. And now let's find the derivative. Oh goodness. It's too much work to do in 2 minutes, and expect everyone to do it. So we'll start with this example on Tuesday. There'll be a homework assignment on the graphing over the weekend, and we'll hold off on this. We'll start here next Monday. Okay, thank you. I'm going to lunch from 12 to 12:30-ish, and then I'll be in my office if anybody want to come? Somebody signed up. Yes.